What's up, geometry? Thanks for tuning in for another episode of Math with Mullins. Today we're going to look at lesson 8.4. This is our final lesson in chapter 8, Proportionality Theorems. So we'll be able to use the triangle proportionality theorem and its converse in addition to other proportionality theorems. We're going to start off with the triangle proportionality theorem, and it states, if a line is parallel to one side of a triangle, intersects the other two sides, then it divides the two sides proportionally. So that just means if I set up a proportion where RT is over TQ, then it would be equal to the same proportion of RU and US, just as long as TU is showing parallel to QS. The converse of that just states if your two lines divide two sides of a triangle proportionally, then you can prove that it's parallel. So using that same statement but just going backwards, if RT is equal to TQ and proportionally it is equal to RU over US, then TU is parallel to QS. Okay, so what we're going to do is try two examples here. In the diagram, we already know that WZ and XY are parallel. If WX is 12, VZ is 10, and ZY is 8, what is the length of VW? Well, when we look at our two proportional theorems, we can know that the proportional or the ratio of x to 12 should be equal to 10 to 8. So when I cross multiply here, I get 120, and dividing that by 8, I'm going to get my answer of 15. Next, it does show that we have two parallel lines, so find the measurement of YZ. So we can just say that is x. We can maybe even say x over 36 is equal to 35 over 44. What we would do next is cross multiply. I'm going to take that 36 and multiply it with 35. I'm going to get, 36 times 35, 1,260, and then divide that by 44. I'm going to get a decimal here, so you can write it as a decimal, 28.63 repeating, or if you wanted to keep it as a ratio, 1,260 over 44, which you can simplify by 4 and get 135 over 11. So either one of these ratios works. The contrapositive of the triangle proportionality theorem, this just meaning we're proving things that are false. If RT to TQ does not equal RU to US, then TU will not be parallel. And if TU is not parallel to QS, then these following things will not be proportional. This one is basically just used to prove if the lines aren't parallel. Okay, so we're going to try one of those here. On the shoe rack, BA is 33, CB is 27 centimeters, CD is 44 centimeters, and DE is 25 centimeters. Explain why the shelf is not parallel to the floor. So what I would do is I'd first set up my proportion. If 27 over 33 is equal to this 44 over 25, then I would know it's proportional or parallel. 27 times 25 is 675, and 33 times 44 is 1,452. So the shelf is not parallel to the floor since the corresponding sides aren't proportional. Okay. Up next, we have the next theorem we'll talk about, which is the three parallel lines theorem. This just states if three parallel lines intersect two transversals, then they divide the transversals proportionally. So we can notice that UW is congruent and YW would be proportional to VX and XZ. So again, we're going to use that setup and solve for some missing sides. So in the diagram, we have our three parallel lines. We have parallel lines for F, G, and H, or they're starting in F, G, and H. In the diagram, angles 1, 2, and 3 are congruent, and GF is equal to 120 yards, which is already labeled. DE is 150 yards, and CD is equal to 300 yards. Find the distance HF between Main Street and South Main Street. So here's Main Street all the way down to South Main Street, okay? So what I would probably do here is start with my proportion. This would be my missing piece. So I would have maybe x over 120 is equal to 300 over 150. I'm going to cross multiply. 120 times 300 is going to give me 36,000. And then I'm going to divide that by 150. And I'm going to get 240. But that is just telling me how far it is from H to G. I want to know from Main Street all the way to South Main Street. So what I would do is I would take, to find the length of HF, I would take 120 plus 240, and I would get 360 yards. Okay. Flipping over on the back, we have some more 3 parallel lines. Let's go ahead and look at these. I want to know the length of BD, which would be here. So again, I can maybe set up 16 over 40 and should be equal to x over 30. Cross multiply, 16 times 30 is 480. And then 480 divided by my 40 is 12. Next, I want to know JM. So 16 over 15 and then x over 18. Cross multiply first. 16 times 18 is 288. And then dividing that by 15, we get 19.2. Okay. The last theorem we're going to discuss today is the triangle angle bisector theorem. If a ray bisects an angle of a triangle, then it divides the opposite side into segments whose lengths are proportional to the lengths of the two other sides. So AD and DB will be proportional to CA and CB. So again, we'll set up a proportion using the angle bisector theorem with these two examples. So it is bisecting. We're seeing that here in angle V. So that means I can set up a proportion. 14 over x can be equal to 24 over 48. The way that I'm setting up these proportions, there's more than one way to do that, just as long as you are still keeping the same pattern with your proportion. For this one, I'm going to multiply 14 times 48. I'm going to get 672. Then I will divide by 24 to get 28. The last one is an interesting one because it has 4 square root 2, and then we have our missing piece. So we can still set this up as a proportion. Let's do 4 over 4, and then 4 square root 2 over y, okay? When you cross multiply here, you're going to have 4y is equal to 4 times 4 is 16, and then square root of 2 just hangs out with itself. Then I'm going to divide both sides by 4, but 4 can only be divided into the 16 here. Since square root 2 is going to be an irrational number, I'm going to have 16 divided by 4, which is 4, and then square root 2. Okay? That'll be all for our lesson today. Thanks so much for tuning in for another episode with Math with Mullins. Hopefully this video helped you, and we will catch you next time when we discuss our Chapter 8 test review. Have a great day.